This is problem 5-69. It's on page 307. And let's see, I'll just draw it for you. Not too bad of a problem, but this is the first problem we've seen that has a distributed load that increases over its distance. So for 1.2 meters, the distributed load increases and then remains constant at 8 kilonewtons per meter. Now there's a support on this side, I'll call that support A, and this one I'll call B. Okay? So the first thing, of course, before we get shear and moment diagrams is to solve for the reactions. That's pretty straightforward. Summing moments at A, the sum should come up to 0. Well, what I did is I calculated the area of this triangle. Okay, so that's 1.2 meters multiplied by 8 kilonewtons per meter divided by 2. That's the area of that triangle, right? So that's the resultant. Where does that resultant act? Do you guys remember?
Third over.
A third over from here or 2/3 over from here, right? Okay, you guys don't remember that, right? All you need, if you have some weird area, how you locate that resultant is just by the centroid. Think of it as a balance point. It's wherever you can put your finger in the area with balance. Okay, that's what it is. So yeah, it's a third over. So let's see. Now, so if I want the moment arm from this end, if I'm summing moments about A, then it's 2/3 of the distance of 1.2 meters. And let me put a negative sign over here because, of course, this moment is going to be a negative moment, right? That resultant will cause a clockwise rotation. So 1.2 meters times 2/3. Okay, so there's the moment caused by the triangular load area. Now the moment caused by the rest of the distributed load is also a negative moment. It would act over at 1.2 plus 1 meter. So that's 2.2 meters. That's its moment arm. And the magnitude would be 8 kilonewtons per meter times 2 meters. So you see how that's 16 kilonewtons. Does that make sense to everybody? Okay. Now the only thing supporting this is the reaction at B. So that's going to cause a positive moment. So force B multiplied by distance, 3.2 meters, should allow us to solve for B. Okay. So 1.2 plus 2 is 3.2. So finally, the reaction at B comes out to 12.2 kilonewtons. Okay. And then, if we do the same thing, some moments about, it's terrible. Some moments about B, taking counterclockwise as positive, we should get 0. And of course, what you end up with is the reaction at A. When I did that, I found that it was 8.6 kilonewtons. If you add the 8.6 to 12.2, well, then you get what? 20.8 kilonewtons. And if you add up all of this load, this distributed load, it's 20.8 kilonewtons as well. So the summing forces give you 0. So let me just sketch the, excuse me, let me replace these with the magnitudes of their loads, 8.6 kilonewtons and 12.2 kilonewtons. Okay? Now, the shear diagram is next. And the shear diagram, should be fine, just a little more space. The shear diagram will be measured in kilonewtons. Okay, and so we start, if we just cut the beam to the right, then we'd have to pull down on the beam with a force equivalent to this 8.6 kilonewtons. So it begins at 8.6 kilonewtons. This distributed load acts from here to just this 1.2 meter line. But notice we're adding more and more and more load. We're adding load quicker as we move over, okay? So you tell me, should this be concave down or concave up? What do you think?
Down.
Down, that's right, because the change is quicker on this side. Does that make sense? So it should be concave down. Now that's another problem. I just noticed I drew a, 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 line that is straight. I need a concave down line here. Well, how far down will it go? Well, again, that's just a matter of computing this area, right? Because this area represents the total amount of load in that distributed area. Okay, so let's make a note that this is concave down. Okay, so when I calculated that area, I came up with, let's see, I don't know what I came up with. It came down to 3.8 kilonewtons. That's how far down it came, so I should draw this a little farther down, something like this. So take 1.2 multiplied by 8 and divide by 2. And what do you get? I should be able to do that in my head. 4.8. I'm sorry, 4.8? Yeah, 4.8. So 4.8, yeah, that makes sense. So it came down 4.8. Okay, so then from here to the end, the distributed load is just constant. It's 8 kilonewtons per meter. And so basically the rate of change of this shear diagram will be constant. And let's see, let's just draw it. Something like that. Should be a straight line. Now I didn't do a good job because those two should be continuous. Notice that this line now, basically the magnitude here basically represents the slope, and the slope at this point is the same on either side because it's that 8 kilonewtons per meter. So this should come down and should be tangent here. Anyway, so this area is 8 times 2 is 16. So it comes down 16 from 3.8. When I did that, that came out to negative 12.2 kilonewtons, which is a good thing because the final load is 12.2 kilonewtons. But then I wanted to calculate the location of this contact point, this crossing. And so what I did is I just took the 8, let's see, actually what I did is I took 3.8 kilonewtons, which is the magnitude of the shear here, and divided it by 8 kilonewtons per meter. Basically asking the question, how many meters of this 8-kilonewton load do I need to come up with 3.8 kilonewtons worth of force? Does that make sense? When I plugged in the numbers, what I found is that I needed 0.475 meters, which makes sense, because a half meter's worth would give you 4 kilonewtons, right? I don't need a total of 4 kilonewtons, I need 3.8. So something less than a half, but close, makes sense. Okay, so basically what that tells me is that the distance here is 0.475 meters. Okay, that's not all of it though, because we also need the moment diagram, and that's in kilonewton meters. Okay, this curve I can do like this. So here's x in meters, x in meters. Okay, notice that there's no moment initially. Okay, so we have to start at 0. And now we have to add up area. Now, I just realized that I made a mistake on this problem because I was thinking this was a straight line, but it isn't. So I'll have to have your help to solve this. Let me make a note that I need to revisit this one as well. But we can solve it here. It may take us a little while, but we'll get it done. The key is to realize that the moment is the integral of the shear over the distance. Okay? That's what we have to do. We have to somehow integrate this. So we need a function that will give us the shear as a function of position. Okay? So the shear will be the integral of the load over distance. This is a distributed load. Okay? If it's a point load, you don't have to integrate it like that. You just add it. But or it just makes step changes in the shear. But now we have to actually integrate this. So let's figure out an equation for this distributed load. Now you have to be careful. Here's what's a little confusing. On this diagram, we'll use a normal coordinate system, positive y in this direction. So this is a negative load. Does that make sense? So our distributed load, W, as a function of position, will have to point downward. We'll need a negative sign so that when we plug it in here, it integrates properly. Okay? Anyway, let's figure that out first. It should be pretty simple, right? Because all we really need is a slope. The slope is going to be 8 kilonewtons per meter divided by 1.2 meters, because we increased by 8 kilonewtons per meter over a distance of 1.2 meters. So then plug in x, and that should be it. Now let's check and make sure this works. At x equals 0, we get a distributed load of 0. Fine. At x equal 1.2 meters, the 1.2 meters cancel 8 kilonewtons per meter. Okay, so there's our distributed load equation that we need to integrate. So if we were to integrate, what is 8 over 1.2? Anyone have that handy?
6.6.
6.6, thanks. So 6.6 kilonewtons per meter squared. If we integrate that, then what we would end up with is, oh, I need an x in there, don't I? X dx. Okay. Do you remember how constants just come out? What happens to the units when a constant comes out of an integral? Nothing. It's just constant also, right? So it just comes out as well. Okay, so the units just come out. What is the integral of x dx? That's what we're left with. Does anyone remember that? X squared over 2, right. Okay, and since I'm setting this up as an indefinite integral, I'll just say plus some constant, and I'll use the boundary conditions to make it work the way I want. What do I mean by that? Well, I know the value of the shear here. It should be 8.6, right? I know the value of the shear here. So I can calculate the value of the constant based on, say, this point, which will be easy, and then verify that it works here. Okay? So let's see, let me make a note. W, the distributed load, is 6.6 kilonewtons per meter squared times x. So that way I've got this equation. If we need to refer back to it, we still have it. All right, so 6.6 over 2 is going to be 3.3. Let me drop the units for now. X squared plus c. I need this to come out to 8.6 when x is 0. Well, that's easy. Hang on, let me think for just a second, make sure I've got everything right. I feel like I should have a first order term, but I know I don't. Okay. All right, so when x is 0, well, this is just gone, and so c is just 8.6. Does everybody see that? Does that make sense? Except I think I'm going to have a sign error because remember, again, the distributed load should have a negative sign on it because it's pointing downward. So then when we integrate it, we'd have a negative sign here and a negative sign there. That makes sense because as x increases, we want the shear to actually decrease. So let's check and see if this works. We know that this position is x equals 1.2. Now, I can't do this in my head, but you can do it on your calculator. 1.2 squared plus 8.6. What do we end up with? 8.6 minus 3.3 times 1.2 squared. Hopefully gives us 3.8. Not, I got to rethink this. Does it work? See a couple people saying yes. Okay. So I'm pretty confident in this equation for the shear. This is the shear as a function of position x. Okay. So now I should be able to integrate it again to come up with the moment. So let's see. Negative 3.3 x squared, here we go, plus 8.6 dx. If I integrate that, what do I get? Well, again, I can pull out the constant and just integrate these two terms separately. Let's see, negative 3.3 x cubed over 3 plus 8.6x plus some other constant. Let me call it C2 so I can differentiate. Now, before I forget it, let's not just say concave down. Let's write the equation here. This would be negative 3.3 x squared plus 8.6. That's the equation of that curve. Okay. Anybody lost? Are we still okay? Questions? All right. I assume you've done this before, correct?
No.
Not this hard? Okay. You know, though, that the moment is the integral of shear, for example, right? So what I'm doing makes sense? Mm-hmm. Okay. All right. Then let's continue. And please do stop me if you have any questions along the way. All right, now let's see. We know that, we've got to figure out the value of that constant. And so we know that the moment at the end is 0. right? So if we plug in x equals 0, we should end up with a moment of 0. So that means C2 is 0. Okay. Now let's check and make sure that, well, we don't have anything to check against, do we? But as we go along, there will be a check built in. So when we go to this point, the moment is going to increase. So go ahead and plug in 1.2 for the value of x here. So the moment evaluated at x equals 1.2. Have you guys seen this notation before? What that means? Okay, this bar means evaluated at. Notice the moment is a function of x. So in other words, plug in 1.2 in here. That's what this says. And what do you get? Okay. So plug in 1.2 for x cubed over 3 times negative 3.3 plus 8.6 times 1.2. What do we come up with for the value of moment at x equal 1.2?
I got 8.4.
8.4?
Got that too.
All right, thank you. So basically, the moment should go up to, let's see, let me think for a second. I think that's going to end up being, yeah, that won't be the highest one. So 8.4, and of course, since we're adding more area at the beginning than at the end, this will also be concave down. But this is an even more extreme curve than this. Notice that this is a second order. Now your author says a second degree. I don't agree with that terminology. I think order is the more appropriate word, but some people use the two interchangeably. Basically, this is an x squared type of polynomial, whereas this curve is an x cubed type of polynomial. Okay? So your author would say that this is a second degree. I would say it's a second order. Use whichever terminology you want. It'll make sense in this class. I'm not going to be picky about that. But this, you need to know this is a third order curve equation, okay? Because of that x cubed term. Okay, the next thing to do is to add moment in the amount of this area. So I'll need your help with this. 0.475 times 3.8 divided by 2 is how much? Since it's getting messy, I'll change to green for the areas.
0.9.
0.9. Anyone agree with that?
Yes.
Is it exactly 0.9?
0.9025.
9025. The only reason I want more decimal places is I know we should end up at a moment of 0, and I want to see if this one's correct. Okay, so let's go on. This area we should be able to compute as well. All we have to do is take 12.5 multiplied by, well, this is going to be a little more tricky, right? 1.5 plus, here, let me write it down. 1.525 meters. That should be this distance because that's what remains of the 2 meters. Okay. Multiplied by 12.2 and then divided by 2 is how much?
$9.3025.
9.3025. Okay. So what's going to happen? Well, this is positive area. So I would expect a second order curve now to continue to increase. Okay, so this one's second order. Why is it second order? Well, because this is a first order line, right? This is an x to the first power. So the integral of that should be an x to the second power type of curve. Would this be concave down? Yes. Because notice that we're adding a lot of area at the beginning, but that's decreasing. So concave down. Okay. So the number we've got, this 0.9025, if you add that to the 8.4, not 8.5, but 8.4, what would you get? That would be what, 9.3025? And fortunately, this is 9.3025. And so my note's in the way. So we come back to 0, which is what we expect at the end of the beam, is a 0 moment. Okay? I think what happened when I calculated this, of course I missed that this was concave down, so I didn't perform the integration, I just used a straight line segment. I ended up with a small moment at the end, I thought, okay, that's just round off. Well, I shouldn't have done that. I should have known, no, I'm carrying 4 decimal places, so it should come out to exactly 0 at the end. Okay? Questions, comments? All right.